In this class, we look at the simplex table for minimization problems. We consider the same example that we used in the graphical and in the algebraic method to solve minimization problems. So, minimize 7x1 plus 5x2 subject to x1 plus x2 greater than or equal to 4, 5x1 plus 2x2 greater than or equal to 10, x1, x2 greater than or equal to 0. Now, these inequalities are now converted to equations by adding slack variables. Because we have a greater than or equal to constraint, we add a negative slack here minus x3 with x3 greater than or equal to 0. And because we have this greater than or equal to constraint, we add a minus x4 with x4 greater than or equal to 0. So, after the addition of the two slack variables, negative slack variables, we get these two equations. When we solved a maximization problem, we started with the slack variables as the initial basic variables because we were able to get a solution. Now, we try to start with x3 and x4 as the basic variables to begin with, and if we take the first constraint or first equation and write in terms of x3, we realize that if x1, x2 are non-basic and they are at 0, we realize that x3 takes a negative value. We realize that x3 now takes a negative value, so x3 becomes equal to minus 4. So, we will not be able to start the solution with x3 and x4. Another way of looking at it is, if we started with x3 and x4 and if we left out x1 and x2, we would have a solution x3 equal to minus 4, x4 equal to minus 10, with which we cannot start the simplex table. The simplex table should start with a basic feasible solution. This would give us an infeasible situation. So, what we do now is, we observed that if we had a positive slack variable, a slack variable with a plus 1 coefficient, then we could have started with that. But the greater than or equal to constraint does not give us the scope to add a slack variable with a positive coefficient and non-negative. So, we do not have that opportunity, and therefore, only for the sake of starting the simplex table, we add two variables. Now, only for the sake of starting the simplex table, we add these two variables. We put a plus a1 and a plus a2 in these two equations. Now, these variables are called artificial variables because they do not belong to the problem. In a way, the slack variables belong to the problem because if the problem has this inequality, and if I am writing this inequality as an equation here, then automatically the slack variable comes. So, it is part of the problem. Now, these artificial variables are not part of the problem. They are introduced only for the purpose of starting the simplex table. So, we introduce two artificial variables a1 and a2, and now we can start the simplex table with these artificial variables. Now, we know that the slack variables do not contribute to the objective function. Now, we have to find out what is the contribution of the artificial variable to the objective function. Now, to understand that, let us go back to the problem without the artificial variable. So, when we look at this problem without the artificial variable, I have a problem here which is the given problem which does not have a1, a2. Now, I have added a1, a2 to this problem and I am going to solve this new problem that has a1 and a2. If I have to find the solution to the old problem and the old problem does not have a1, a2, then obviously the solution to this problem should not have a1, a2. But I have introduced a1, a2, and therefore it is my responsibility to make sure that when I solve this problem, the solution, if it exists, does not have a1, a2. How do I do that? What I do is, I give a large objective function coefficient to A1 and A2. This big M is large. This big M is like, if I look at the other values like 7, 5, 0 and 0, big M is large. Big M is 100. Big M is 1000. Big M is 10,000. It's a very large value. So big M is used as a notation to represent a very large positive value that tends to infinity. Very large value. So if I put a very large coefficient for A1 and A2 and I am minimizing, it is very likely that A1 and A2 will not come in the solution. There will always, if this problem has a solution, then the objective function value of that will be smaller compared to a solution that would involve A1 and A2. Therefore, it is likely that A1 and A2 do not come into the solution. So I have introduced A1 and A2 for the sake of starting the simplex algorithm. At the same time, I am giving a very large positive value to the objective function so that in the solution A1 and A2 do not come. So if the original problem has a solution, the same solution will come, and solutions involving A1 and A2 will not come because they would have higher objective function values, and I am trying to minimize. So with this, let us go and set up the simplex table. So we set up the simplex table, we look at this problem with the A1 and A2 and we set up the table. In the previous example, we have solved it for a maximization problem. Now we have a minimization problem. So it is easy to write a minimization problem as a maximization problem by multiplying the objective function with a -1. So I will set up by saying, now the variables are here, x1, x2, x3, x4, a1, a2. There are 6 variables. You can see the 6 variables are here. The objective function coefficients are written with a negative sign because they are written for a maximization problem. So this 7 becomes -7, -5 and so on. Now I realize that the way I have written this, my identity matrix is coming with A1 and A2 because they have been inserted into the problem for a starting solution, and therefore they will have an identity matrix there. Therefore I will start the table with A1 and A2 as my first set of basic variables. The objective function coefficients are -m and -m, which are taken from these two positions. Now I find Cj minus Zj. Now what is Z1? -m into 1 plus -m into 5, which is -6m. So C1 minus Z1 is -7 minus -6m, which is 6m minus 7. Now you will observe that I am not giving an explicit value to this m. There are two ways of doing it. I can give an explicit value to m. Because the other coefficients are smaller, like 7 and 5, I could have given m is equal to 100. But then if there were some other problems where these coefficients are large, now m should be bigger than that. Therefore, I am simply using m as a number which is large, positive and tends to infinity. So I am writing it as 6m minus 7. If m is 100, then this will become 593. But I am not writing an explicit number, I am still writing big M as a notation to represent a large number. Now C2 minus Z2 is minus m into 1 plus minus m into 2 is minus 3m. So minus 5 minus minus 3m is 3m minus 5. Minus m into minus 1 plus minus m into 0 is plus m. So 0 minus m is minus m. Minus m into 0 plus minus m into minus 1 is plus m. 0 minus m is minus m. Minus m into 1 plus minus m into 0 is minus m. Minus m minus minus m is 0, and similarly it is 0. The basic variables will always have 0 value for Cj minus Zj. The basic variables will always have 0 value for Cj minus Zj. Now the value of the objective function is minus m into 4 plus minus m into 10, which is minus 14m. But it is customary that you don't write it. You simply put a dash here when you have these artificial variables in the solution. After all, we don't want them, and therefore when they are there, we don't write the objective function value. We simply keep it as dash. So this completes part of the first one. We now have to find out whether there is another variable that can come into the solution. So now we look at the Cj minus Zj values. So we find that variable which has the largest positive Cj minus Zj. Now this is a negative value, this is a negative value. These two are positive values. As m is large, both are positive values. If m is infinity, then both are infinity. But if m is large and not infinity, 6m will be bigger than 3m. And 6m minus 7 will be bigger than 3m minus 5 because m is sufficiently large. Therefore, the most positive Cj minus Zj happens to be for x1, and the variable x1 will come into the solution. Now x1 will come into the solution and it has to replace either a1 or a2. To do that, we find the ratios 4 divided by 1 and 10 divided by 5. So 4 divided by 1 is 4, 10 divided by 5 is 2, and the limiting value is the minimum of these two ratios, and therefore this variable a2 will leave the solution and the variable x1 will replace the variable a2 into the solution. Now I have shown the first table where the variable x1 is replacing the variable a2. Now we have to do the next iteration. So variable x1 has replaced variable a2. So we write the two, x1 has replaced a2 and a1 continues to be there. So x1 and a1 are our basic variables. The objective function coefficients are minus m and minus 7 from the first row that we have. Now this element, which is the intersection of the entering variable and the leaving variable, which is shown in a different color, this is your pivot element, and this row is your pivot row. So as we did previously, divide every element of the pivot row by the pivot element. So 5 divided by 5 is 1. Remember that this is the second row is the pivot row, so I write the second row first. So 5 divided by 5 is 1. 2 divided by 5 is 2 by 5. 0 divided by 5 is 0. Minus 1 divided by 5 is minus 1 by 5. 0 divided by 5 is 0. 1 divided by 5 is 1 by 5. And the right hand side is 10 divided by 5, which is 2. Now this 2 is the same as this 2, which was also obtained as 10 divided by 5. Now we have to write the A1 row, the first row. Now this x1 has become a basic variable, therefore this should have 0, 1. 1 is already there, I need a 0 here. I also have to retain the 1 here, because A1 continues to be. I also have to retain the 1 here because A1 continues to be a basic variable. So I need a 0 in this position. So I look at the previous one, which is 1. So 1 minus 1 will give me 0. So this number minus this number will give me the value that I should have in this position. So 1 minus 1 is 0. 1 minus 2 by 5, 3 by 5. Minus 1 minus 0 is minus 1. 0 minus minus 1 by 5 is plus 1 by 5. 1 minus 0 is 1. 0 minus 1 by 5 is minus 1 by 5 and 4 minus 2 is 2. So we have now completed this and we have to write the Cj minus Zj values. So we write the Cj minus Zj. So minus m into 0 plus minus 7 into 1 is plus 7. So minus m into 0 plus minus 7 into 1 is minus 7. So minus 7 minus minus 7 is 0. The basic variable will always get a value 0. Second one we have to write carefully. Minus m into 3 by 5 minus 3m by 5 minus 14 by 5. So minus 5 plus 3m by 5 plus 14 by 5, which on simplification will give us 3m minus 11 by 5. Minus m into minus 1 plus minus 7 into 0 will give us plus m. So 0 minus m is minus m. Minus m into 1 by 5 plus minus 7 into minus 1 by 5 is minus m by 5 plus 7 by 5. So this will become m minus 7 minus m by 5 with a minus sign. So I will have a minus sign here. So it will become, no, I don't have a minus sign here. Just erase it. So I get minus m by 5 and 0 minus m by 5 is plus m by 5, which comes here. And here I have plus 7 by 5. So 0 minus 7 by 5 is minus 7 by 5. So m minus 7 by 5 is correct. Fifth one, minus m into 1 is minus m plus 0. So I will have a 0 there. I will have a 0 here because it is a basic variable. For the last one, plus m by 5 minus 7 by 5. So minus m by 5 plus 7 by 5 will become minus 6m plus 7 by 5. The value of the objective function is again written as dash because there is still an artificial variable in the solution. So it becomes dash. Now again we want to check whether we have to stop here, whether the optimum solution is reached or whether we need to proceed further. So the most positive Cj minus Zj will enter. So this is negative, this is negative. 3m minus 11 by 5, m minus 7 by 5. 3m is bigger than m. Therefore variable x2 will try to come into the solution. Now when variable x2 tries to come into the solution, it has to replace either a1 or x1. To do that, we find out the limiting values. 2 divided by 3 by 5 is 2 into 5 by 3, which is 10 by 3. 2 divided by 2 by 5 is 2 into 5 by 2, which is 10 by 2, which is 5. The smaller value is 10 by 3. So that is the limiting value. So variable x2 will come in and variable a1 will go out. Now I have shown the entire thing. Both the tables I have shown. Variable x2 will come into the solution and variable a1 will go out of the solution. So this number shown in a different color is the pivot element. So we now write the new basic variables, which happen to be x2 and x1. x2 has come in and has replaced a1. So we write x2 and x1. The objective function values are minus 5 and minus 7 from this part of the table. Now we have to write this row first. The pivot row has to be replaced. So divide every element of the pivot row by the pivot element. So the first row is written by dividing every element by 3 by 5. So 0 divided by 3 by 5 is 0. 3 by 5 divided by 3 by 5 is 1. Minus 1 divided by 3 by 5 is minus 5 by 3. 1 by 5 divided by 3 by 5 is 1 by 3. 1 divided by 3 by 5 is 5 by 3. And minus 1 by 5 divided by 3 by 5 is minus 1 by 3. 2 divided by 3 by 5 is 10 by 3. So the first row is written. Now we have to write the second row. Now to do that, we have this variable x2 coming here. So this should have a 0 here. It should have a 1 0. x1 should have a 0 1. x2 is the one that has come in now. So I should get a 0 here. So to get a 0 here, I look at the corresponding position, which is 2 by 5. So this minus 2 by 5 times 1 is 0. So 2 by 5 minus 2 by 5 times 1 is 0. So we use that. 1 minus 2 by 5 times 1 minus 2 by 5 times 0 is 1. 2 by 5 minus 2 by 5 times 1 is 0. 0 minus 2 by 5 into minus 5 by 3 is plus 2 by 3. Minus 1 by 5 minus 2 by 5 into 1 by 3 is minus 1 by 5 minus 2 by 15. So minus 1 by 5 is minus 3 by 15, minus 2 by 15 is minus 5 by 15, which will become minus 1 by 3. 0 minus 2 by 5 into 5 by 3 is minus 2 by 3, and 1 by 5 minus 2 by 5 into minus 1 by 3 is 1 by 5 plus 2 by 15, which will become plus 1 by 3. 2 minus 2 by 5 into 10 by 3 is 2 minus 4 by 3. So 2 minus 4 by 3 is 2 by 3, which is shown here. Now we have to check whether this solution is optimum, or we have reached the optimum here, or do we need to go further. To do that, we have to find the Cj minus Zj values. So we do Cj minus Zj. So minus 5 into 0 plus minus 7 into 1 is minus 7. Minus 7 minus minus 7 is 0. Z2 is minus 5 plus 0 is minus 5. C2 minus Z2 is minus 5 minus minus 5, which is 0. So the basic variables will have 0 value. Here it is plus 25 by 3 minus 14 by 3, which is plus 11 by 3. 0 minus 11 by 3 is minus 11 by 3. Here it is minus 5 by 3 plus 7 by 3, which is plus 2 by 3. So 0 minus 2 by 3 is minus 2 by 3. Now here it is minus 25 by 3 plus 14 by 3, which is minus 11 by 3. So minus m plus 11 by 3. So it's minus m plus 11 by 3, which is minus 3m by 3 plus 11 by 3. The last one is plus 5 by 3 minus 7 by 3 is minus 2 by 3. So it becomes minus m minus minus 2 by 3 is minus m plus 2 by 3. So this will become minus 3m plus 2 by 3. The value of the objective function, now we calculate minus 5 into 10 by 3 minus 50 by 3 minus 14 by 3 is minus 64 by 3. Now we need to check whether there is any positive Cj minus Zj. Now we have 0, 0, negative, negative. Minus 3m plus 11 by 3 is a negative quantity. Minus 3m plus 2 by 3 is also a negative quantity. So all of them are negative. No variable is entering. Therefore the algorithm stops by giving us a solution x1 equal to 2 by 3, x2 equal to 10 by 3, objective function equal to minus 64 by 3. But we have to remember that we had converted a minimization problem to a maximization problem by multiplying with a minus 1. Therefore, we have to multiply back with a minus 1 for the minimization and say that the objective function value for the minimization is plus 64 by 3, while for the corresponding maximization it was minus 64 by 3. So when we solve a minimization problem as a maximization problem, we will get a negative value, and finally we have to make it positive. So the optimum solution is x1 equal to 2 by 3, x2 equal to 10 by 3, and objective function is 64 by 3 for the minimization problem. So this is how the simplex table works for the minimization problem. When we have greater than or equal to type constraints, we will have negative slack variables which cannot become starting variables for the solution. So we add artificial variables, and when we add artificial variables, we will have this involving the minus m for maximization and plus m for minimization. So this method is also called big M method because we are using the big M in solving these problems. So whenever we have greater than or equal to constraints, we will be adding the artificial variables, and most minimization problems will have greater than or equal to constraints, and therefore we use this big M method to solve minimization problems using the simplex algorithm. Other aspects of the simplex table we will now see in subsequent classes.